morning, students.
It is visible, sir. You can start. It's 9:40.
Okay. So these are the basic requirements. Please follow these instructions when attending the session. Okay, now we'll start the session. So before starting the today's session, we will discuss about what the content has discussed in the previous sessions. So in the last session, we have discussed about digital logic gates and different logic operations. Okay. And then we have
Hello,
discussed about symbols. Yes, ma'am.
Selva sir.
Yes, ma'am. Can you?
Sir,
Hello.
sound கொஞ்சம் இது sound கம்மியா இருக்கிற மாதிரி இருக்கு சார். கொஞ்சம் clarity கம்மியா இருக்கு. Students, please respond. Is it audible? Is it clear? No, sir, it's not clear. No, not clear, sir. Sir, sound கொஞ்சம் ஒரு எக்கோ இருக்கு சார். எக்கோ இருக்கு, கொஞ்சம் பின்னாடி இருந்து கேக்குது சவுண்ட். Sir, same problem, sir. Okay. Sir, கொஞ்சம் கண்டினியூ பண்ணுங்க சார், சொல்றேன். கொஞ்சம் தொடர்ந்து பேசுங்க சார்.
In the last session, we have discussed about symbols for logic operations and symbols for logic gates. So, almost 7 logic gates are discussed in the last session. So, what kind of symbol can be used for logic operations and to represent logic gates? Which kind of symbols we can use?
Sir, sorry, sir, sorry. Not Selva, sir. Sorry, not clear, sir. சார் இல்ல சார். சார் கொஞ்சம் கிளாரிட்டி இல்லாததா இருக்கு சார். கிளியர் ஆகல நீங்க பேசுறது.
சுமி மேம் கிளாஸ் ரூம்ல சார் இருக்காங்களா? சுமி மேம்
ஹலோ ஆன்சி மேம், என்ன மேம்?
சார் கிளாஸ் ரூம்ல இருக்காங்களா?
கூகுள் கிளாஸ் ரூம்ல இருக்காங்க மேம்.
இல்ல இல்ல மேம், நம்ம கிளாஸ் ரூம்ல இருந்தா விண்டோஸ் க்ளோஸ்டா இருந்துச்சுன்னா ஓபன் பண்ணி விடுங்க சார்.
ஓகே ஓகே. செல்வா சார், சார் கேக்குறீங்களா சார்? செல்வா சார், சார் கிளாஸ் ரூம்ல நல்லா எக்கோ வருது சார். மேம் சொல்றாங்கன்னா என்ன சொல்றாங்கன்னா கொஞ்சம் விண்டோஸ் ஓபன் பண்ணி விடுங்கண்ணா. சார் சவுண்ட் ரொம்ப பின்னாடி இருந்து கேக்குது சார், லைட்டா எக்கோ வருது. ஹலோ சார். நோ சார். சார் உங்க வாய்ஸ் கேக்குது, ஆனா சார் கிளாஸ் இருக்கும்போது கிளாரிட்டி இல்ல சார். நீங்க பேசுறது கிளாரிட்டி இல்ல. அது இல்லாம ரூம்ல நல்லா எக்கோ வருது. சார் சார் ஸ்டூடெண்ட்ஸ் நீங்க யாராச்சும் கொஞ்சம் மைக் ஆன் பண்ணி பேசுறீங்களா? உங்களுக்கு எப்படி இருக்கு?
Ma'am, not clear, ma'am.
Okay. Sir, it's not clear, sir. சார் சேம் ப்ராப்ளம் இருக்கு சார். சார் கேக்குறீங்களா? சேம் இஷ்யூ சார், சேம் ப்ராப்ளம். Sir, பின்னாடி device on ஆயிருக்குங்களா sir? முகுந்த் சார், முகுந்த் சார் கேக்குறீங்களா சார்?
மேம் சொல்லுங்க மேம். மேம்
சார் சார் ப்ராப்ளம் இருக்கு சார். சவுண்ட் கிளியர் இல்ல சார். நல்லா எக்கோ வருது.
எப்போ வருது? மேம் இப்போ ஓகே சார், கேக்குது. இல்லை சார் கேக்குது. கிளியரா ஓரளவுக்கு இருக்கு, பேச ஆரம்பிச்சு. நீங்க பேச ஆரம்பிச்சு.
Okay, so in the last session, we have discussed about different logic gates and symbols used for logic operations and symbols for different logic gates. Okay, and then we have discussed logical operations of each logic gates. Right? So today in this session, we are going to discuss about logical operations on binary numbers and Boolean algebra. Okay, for the two topics, we will discuss about how to minimize some kind of logical expression for simplifying the given logical expressions. Okay, so already we have discussed in this slide. In the last session, we have discussed this slide. So here the logical operation of binary numbers. Okay. So in the last session, we have discussed logical operation on two input data, which are 1 bit in data. But if input data is multiple bits, for example, 8 bit data, then how to perform logical operations? Okay. So here we start with AND operation. So logical AND operation of two 8 bit binary numbers. Okay. So how to perform logical AND operation on two 8 bit binary numbers. Okay. So here I am showing the first input data, that is just n bit in length. Okay. So A0, which is the LSB, A n-1, which is the MSB. Okay. So this is MSB, most significant bit. A0 is the least significant bit.
Hello. Hello, ma'am.
சார் சார்
Voice audible இருக்கா, clear இருக்கா?
இப்ப நல்லா கிளியரா இருக்கு சார்.
Super, ma'am. Okay, ma'am. Okay, so this is my first input A, which is n bit in length. A0 is the LSB, an-1 is the MSB. Okay, we know the expansion for these two abbreviations: LSB, least significant bit; MSB, most significant bit. Okay, then I have a second data, that is B, which is also n bit in length, B0 to Bn-1. Okay, now we are going to perform AND operation on these two n bit binary numbers. Okay, so this is the resultant operation. So result of logic AND operation. Okay, so here we are taking least significant bits of both the numbers. That is A0, B0. Okay, so we are performing AND operation on these two significant bits. Okay, so A0, B0. We are considering two LSB bits of both the data and we are performing AND operation. Similarly, A1, B1, A2, B2 up to AN minus 1 and with Bn minus 1. Okay, so this procedure is called as bitwise logical AND operation, right? Okay, now we will see some example. So here we are having two numbers A and B. Okay, data A, input data B. So we are going to perform logical AND operation on these two input data, which are 8-bit in length. Okay, so perform the logical AND operation of two 8-bit binary numbers A, which is equal to 1 0 1 1 0 1 1 1. Okay, then B, the value of B is 1 1 1 0 1 1 0 1. Okay, so now this is the input data A, this is the input data B. So how to perform logical operation on these two input data? We are going to consider bitwise operation. Okay, so LSB. We are taking first bit. Okay, LSB of both the data 1 and with 1. It will give result logic 1. Similarly, next bits. Okay, 1 and with 0 will give 0 as the output. Next one, 1 and with 1, it will give 1. Similarly, up to MSB. Okay, so you will get result like this. And also note that the result of this bitwise operation is also 8-bit. Okay, here we are taking two 8-bit binary numbers. The resultant number, resultant value is also 8-bit in length. Okay, if you are doing bitwise operation on n-bit length numbers, then result also n-bit in length. Okay, then this logical operation can be used for masking the bits. Okay, so sometimes it is one of the application of logic AND operation. So sometimes we need to perform masking on specific bits of binary number without disturbing other numbers. Okay, so masking means what? Hiding the data or making it 0. Okay, so for example, masks the bits A7, A4, A2 and A1 of an 8-bit binary number using AND operation. Okay, so we have a 8-bit data that is named as data A. Okay, so the bits are named as A0, A1, A2 up to AN minus 1. Here the bit length is 8, then 8 minus 1, 7. So MSB is A7. Okay, so on that 8-bit data, we are going to mask or we are going to make 0. Okay, specific bits that are A7, A4, A2 and A1. Right? So how to perform the masking operation on that 8-bit data? So this is my 8-bit data, A0 to A7. Okay, so masking means what? We are going to make that specific bit to 0. Okay, so how to make that particular bit to 0 using AND operation? If you are performing AND operation, if you want to get 0 on the output, then what we have to do? Any answer? We are going to perform AND operation on a particular data or particular bit. Okay, but we want a result as a logic 0. For example, take this A0. Okay, this A0 LSB may have a 0 or 1, but I need 0 as the result. So what we can do? We have to do AND operation. Okay, so A0 should be ANDed with 0 because we know the logic of AND operation. At least any one of the input is 0, then AND gate produces logic 0 as the output. So we need to perform AND operation with a data 0 or with a binary bit 0. Okay. So here we are going to mask A7, A4, A2, A1. So these 4 bits should be ANDed with 0, right? So A7, A4, A2, A1. Okay, these 4 bits should be ANDed with logic 0. Then only we will mask that particular 4 bits in the result. Okay, other bits are ANDed with logic 1 because we are not interested to disturb other bits. Okay, so we are doing AND operation with logic 1. So the result will be like this. Okay, so here A0 is same as in the given data. Okay, but A1, A2 both are masked with a logic 0. A3 is undisturbed, A5, A6 both are not disturbed, A7 is masked with logic 0. Right? So why we need to perform this masking operation on a particular data? Okay, so if you want to hide our information while sending from one place to another place, okay, while transmitting the data, if you want to hide your information, then you can follow this procedure. Okay, so third party cannot access the data sent through the channel. So that is the purpose of masking the data in binary numbers. So there is another example. Find the bit pattern to mask the bits A5, A3, A2 and A0 of an 8-bit binary number all ones using AND operation. Okay, so 8-bit data. So I'm considering A0 to A7, right? Then what are the bits going to be masked? A5, A3, A2, A0. So that 4 bits are ANDed with logic 0. Then only the particular bits can be masked, right? Then other bit position will be ANDed with logic 1 value, right? So this is my given data all ones. Then my result is like this. So 1 ANDed with 0 will give 0. That means A0 bit is masked with logic 0. A1 is reproduced in the output. A2 is masked. A3 is also masked. A4 is repeated in the output. Then A5 masked. A6, A7 both are repeated in the output. Okay, so here the bits A5, A3, A2 and A0, these 4 bits are masked, right? Then the another kind of logic operation, logical OR operation. Okay, so how to perform logical OR operation on n-bit binary numbers? Okay, this is same as logical OR operation. Okay, so here also we are going to consider n-bit data, 2 n-bit data. Then we are going to perform bitwise OR operation. Okay, LSB of A0, LSB of input data A, LSB of input data B. Okay, that is A0, B0. Okay, these two can be ORed and will give result A0 or with B0. Right? Then A1, B1, A1 or with B1, A2 or with B2. Similarly, up to MSB bits, AN-1 or with BN-1. Okay, likewise, you can perform bitwise OR operation. Okay, logical AND operation, logical OR operation on n-bit binary number follows same procedure, but the logical operation is different. Okay, that is based on the type of logical operation. It may be AND or OR operation. Okay, so we'll see one example. So here we are going to perform logical operation of two n-bit binary numbers A, that is equal to 1 0 1 1 0 1 0 1, and the data B, which is equal to 1 0 1 0 1 1 0 1, right? So this is my input data A, this is my input data B. Then after performing an OR operation on LSB of both input data, okay, A0 B0, that will give logic 1 as the output. Why? Because for OR gate or OR operation, okay, if at least one input is logic 1, then result will be logic 1, right? So here both the data are logic 1, so the result will be logic 1, okay. Then next bit position A1 B1, if you are performing OR operation on A1 and B1, that will give logic 0 as the output, okay. Then next 1 OR with 1, so result will be logic 1. Here the next bit 0 OR with 1, okay. So here in this bit position we are having at least one logic 1 in the input data, so the result will be logic 1. Similarly other bits, okay, up to MSB, right? So 1 OR with 0 will give 1, 1 OR with 1 1, 0 OR with 0, result will be 0, then 1 OR with 1, result will be logic 1, okay. So hope these kind of operations are easy to understand, right? Then like AND operation, the logical OR operations also used for unmasking the bit positions, okay. You can unmask specific bits in a given binary number, okay. Unmasking means we are going to make that particular or a specific bits to logic 1, okay. So for example, unmask the bits A7, A4, A2 and A1 of an 8-bit binary number using OR operation, okay. So this is the bit position of the given 8-bit data A0 to A7, because this is 8-bit data, okay. So LSB is A0, MSB is A7. So we are going to unmask the bit positions A7, A4, A2 and A1, right? So that should be ORed with logic 1, right? So A7, A4, A2, A1, okay. Other bit positions are ORed with logic 0, okay. Why? Why we are ORing the bit positions A1, A2, A4 and A7 to unmask the bit position? Any answer? You can give your answer in the chat box. Sumi ma'am?
No, sir. No answer, sir.
Okay. See, if you are doing OR operation.
So there is
If you are
one
doing
reply, sir,
OR,
sir, from Srihari. Unhiding. He typed right like unhiding.
Yes, the purpose of this operation is for unhiding the bit position, but we are specifically choosing logic 1, okay. For ORing with data bit position A7, we are choosing the logic value 1. Why? See, we are going to unmask the bit position A7, A4, A2 and A1, okay. So these 4 bits can be unmasked at the result, okay. But here for unmasking these 4 bits, we are choosing logic 1 value. Okay, why we are choosing logic 1 for unmasking that particular specific bit? Because we are performing OR operation. Okay, when you are doing OR operation, if one of the bit is logic 1, okay, whatever may be the other bit, okay, it may be 0 or 1. Okay, X means don't care. This value can have either 0 or 1. Okay, this value will be either 0 or 1. Okay, whatever it may be, the result will be logic 1. Okay, so unmasked means we are going to make that particular bit to logic 1, right? So we are ORing with logic 1, right? So like this, A7 is ORing with logic 1, A4 is ORed with logic 1, A2, A1 both are ORed with logic 1. Okay, then your result will be like this. Okay, so A7 is unmasked, or that particular bit position is become logic 1. Okay, A6, A5 that are repeated in the output, A4, A2, A1. These three bits are set to logic 1. Okay, then A3, A0. Okay, it is similar to the input given data, right? So like that, you can unmask the bit positions. That means we can set the logic 1 on the specific input. You can set the logic 1 on the specific bit position of the input data, right? So this is another example. So in this example, we are going to unmask the bit position A5, A3, A2, A0. Okay, for the given data 1 1 0 0 0 0 0. Okay, using OR operation, right? So this is the given data, 8-bit data. So A0 to A7, we are going to unmask the bit position A5, A3, A2, A1. Sorry, A0. Okay, so we are putting logic 1 on that particular bit position. Okay, all other are ORed with logic 0. Okay, then this is my result. Okay, 1 1 1 0 1 1 0 1. Okay, so here just we are doing bitwise OR operation. 0 OR with 1 1, 0 OR with 0 0. Similarly, 1 OR with 0 1. Okay, then the third logical operation is logical XOR operation. Okay, so how to perform logical XOR operation on n-bit binary numbers? Okay, here also same procedure. We are going to perform bitwise operation. Okay, A0 XOR with B0, A1 XOR with B1, A2 XOR with B2 up to AN-1 XOR with BN-1. Okay, if it is a multiple input data, then you can do logical operation on bitwise manner. Okay, so this is the example for logical OR operation on two 8-bit binary numbers. Here we are taking two data, A and B. The value of A is 1 0 1 1 0 1 0 1. The value of B is 0 0 1 0 1 1 0 1. Okay, so here they are going to perform XOR operation. Okay, so remember that XOR operation, if both the inputs are same, then result will be 0. Okay, if both the data, if I am having two inputs, for example A and B, okay, both the inputs having same logic, either it may be 0 or 1, but both the value having same logic. Okay, that means the result will be logic 0. Okay, that is the logical operation of XOR gate, right? So here, if you are considering LSB of input A and input B, both are having same logic, logic 1, logic 1. So the XOR will produce logic 0. right? Then the next one, 0, 0, same logic, so result will be 0. Again, same logic, 1, 1, that also produces 0. Then 0, 1. Okay, different logic on both the inputs. Or you can say the alternative function. Okay, the alternative concept behind the XOR operation. Okay, if the odd number of ones are available in the inputs, then the result will be logic 1. Okay, XOR gate will produce logic 1 when there is a odd number of ones available in the inputs. Okay, so here the data, input A having logic 0, input B having logic 1. Okay, so when you are performing XOR operation on these two inputs, 0 XOR with 1 will give logic 1. Okay, similarly here, 1 XOR with 0 will give logic 1. Here, same data, 1, 1. Okay, same data available on both the input, so the output is 0. Again, 0. Here, the MSB of both the inputs having different logic. Input A having logic 1, input B having logic 0, so the result will be logic 1. Okay, so this is the bitwise XOR operation on given two 8-bit numbers. Okay, then with help of this logical XOR operation, we can perform complement function on given binary number. Okay, if I'm having n-bit binary number, okay, for example A, okay, which is equal to some binary value 1, 1, 1 something. Okay, you can obtain complement of that particular input A by performing XOR operation, right? So here is the example. So complement the bit positions A7, A4, A2 and A1 of an 8-bit binary number using XOR operation. Okay, so this is my 8-bit data of input A0 to A7. Okay, so here they are going to complement the bit positions A7, A4, A2 and A1, right? That means if the value of A7 is logic 0, then I have to make that logic 0 to logic 1. Okay, or for example, it may have logic 1 in the A7 position. If it is logic 1, we have to make that logic 1 to logic 0. So that is the complement operation, right? So how to perform this complement operation using XOR operation, right? So recall the logical operation of XOR operation. XOR. So if it is 2 input logic, 0, 0, 0 will produce 0, 0, 1 produce 1, 1, 0 produce 1, 1, 1 produce 0, right? So this is the truth table of XOR gate. Okay, so here consider these two combinations. Okay, 0, 1, 1, 1. Okay, second and fourth combination, right? So consider this is my input. This first position is my input. Okay, so when you are performing XOR operation with logic 1, then what is my result? 1, 0. Okay, so this is my, if it is my input, then if I am performing XOR operation with logic 1, then the result will be logic 1. Okay, complement of my input 0. Similarly here, my input is logic 1. I am performing logic 1 with again logic 1. So it produces logic 0 as the output. Okay, this 0 output is complement of my input logic 1. Okay, that means when we are doing XOR operation with any input data, okay, using logic 1, then the result will be complement of that input data. Okay, so for example, in conceptual A XOR with 1, then you will get A bar. Okay, so this is the concept. Okay, so if you are performing XOR operation with logic 1, then you will get complement of that input data. Okay, so that's why we are taking logic 1 here. Okay, we are going to complement A7, A4, A2, A1. Okay, using XOR operation. So we are doing XOR operation with logic 1 on these 4 bit positions. Okay, again from this truth table, consider first combination and third combination. Okay, consider this is my input data, this 0 and this 1. Okay, both are my input data. I'm doing XOR operation with logic 0. What is the result? 0, 1. That is equal to my input data. Okay, that means if you are doing XOR operation with logic 0, then you will get the input data again in the output. Okay, it will repeat the or reproduce the input data to the output, right? So this is the output. So if you are doing XOR operation with logic 0, then result will be the given input data. Okay, if you are doing XOR with A0 and 0, then your result will be A0. Okay, but if you are XORing with logic 1, then the given data will be complemented. Okay, A1 will be A bar. Then again here logic 1 is used for XOR operation, so A2 will be A2 bar, here 0, A3, here logic 1, so A4 will become A4 bar, then here 0, 0, so A5, A6 both are repeated in the output, then the A7 bit is complemented, so A7 bar, because we are doing XOR operation with logic 1. Okay, so like that you can perform complement operation using XOR operation. So here is the one example. So here we are taking 8-bit binary number. Okay, on this 8-bit binary number, we are going to complement the bit position A5, A3, A2 and A0. Okay, using XOR operation. So this is the input pattern. So this is my given data. Okay, so to perform complement on A5, A3, A2, A0, we are using this kind of pattern. This is my input pattern, right? Then this is the result. Okay, so A0 bit position having logic 0. So if you want to complement that logic 0, then you have to do XOR operation with logic 1. Okay, so that will produce logic 1 in the output. The given input is logic 0, but the produced output is logic 1. Okay, the complemented output. Okay, again here we are using 0, so the input is repeated here. Okay, again the bit position A2, A3 both are XORed with logic 1, so both are complemented. 0 becomes 1, 1 becomes 0. Okay, similarly the bit position A5. Okay, A5 is XORed with logic 1. Okay, so the input bit A0 is complemented in the output. Okay, 0 becomes 1, right? So like that you can perform complement operation on a given data using XOR operation. Okay, so with this, any doubt? So logical operations and some basic applications of logical operations. Okay, so we have discussed 3 applications: how to mask the bit position using AND operation, how to unmask the bit position, and how to perform complement operation using XOR operation. Right? Any doubt? If there is no doubt,
No,
means
no, sir.
okay. Then we will start with Boolean algebra. So this is the most important concept in the digital electronics. Boolean algebra deals with binary variables, okay, ones and zeros, and logical operations, the basic logical operations, and, or, and not. Okay, so Boolean algebra is one kind of operation which can be performed on binary values, okay, using some kind of procedure, right? So the binary variables may have values like logic zeros and logic ones. Okay, then what kind of operation we can perform? Okay, the basic operations and, or, and not, right? So this is one example animation. Okay, a 0 represents false, okay, 1 represents true condition, right? So this was just for understanding. So true can be represented as logic 1 or vice versa. 1 can be represented as true condition. Logic 0 will be represented as false condition. Okay. Then there are some rules we have to keep in mind while following Boolean algebra on digital electronics. Okay. So variables can have only 2 values. Okay, if there is a binary value, so a binary variable, that binary variable having only 2 values, either it may be 0 or 1. Okay, then logical AND operation can be represented by dot sign, like this: A dot B dot C. Okay, that means A AND with B, again that particular result is AND with again C. Okay, then logical OR operation is represented by plus sign. Okay, A plus B plus C. Okay, here the plus represents logical OR operation. So in Boolean algebra, dot represents AND operation, plus sign represents OR operation. Okay, then logical NOT operation can be represented by 2 manner. Okay, one is by using bar on the variable, another one is prime on the variable, like this: X bar or X prime. Okay, the single quote represents a prime. Okay, so X bar or X prime, both are representing same operation, that is NOT operation. Okay, so these are the basic rules we have to follow while doing Boolean algebra. So Boolean function or Boolean expression. Okay, so Boolean function consists of Boolean variables or binary variables A, B, C or X, Y, Z. Okay, then logical operations and, or, not, and constants, zeros and ones. Okay, and produces 2 possible outputs. Okay, if you are considering any Boolean function which is consists of Boolean variables A, B, C or X, Y, Z, whatever it may be, and we are performing logical operations on that binary variables or with some constant values, then finally we will get the 2 possible outputs. Okay, the output value will be either 0 or 1. It deals only binary values. Okay, zeros and ones. Right. So this is the example for Boolean expression or Boolean function. So which can be represented by f of, function of. Okay, f represents function of a comma b comma c. These are the input binary variables. Okay, in this Boolean function, these are the input variables a, b, c. Okay, then this is the Boolean expression. Okay, with the help of these input binary variables, we are representing certain function. Okay, or certain expression. Okay, that is a dot b plus b dot c prime plus c dot a prime. Okay, so here we are using binary variables a, b, c. Okay, or its complements. Okay, and we are performing again the logical or operation, and operation, not operation. Okay, we are performing basic logical operations and or not operations. Okay, sometimes this expression may have constant. Okay, plus 0. Okay, or and with 1. Okay, like that we may have expression like this. Okay, so this is for example. Okay, this is one kind of Boolean expression representation. Okay, then from this Boolean function we need to know some terms. Okay, so that are binary variables, or simply you can say variables. Okay, that variable can be designated by alphabets such as a, b, c, x, y, z, like that. Okay, you can also use I, j, k, whatever it may be. Okay, you can use any alphabets to represent a binary variable. Okay, as shown in this example. Then the next important term is literals. So what is mean by literals in a Boolean function or Boolean expression? Okay, so literal means each occurrence of variable or its complement, okay, is called as literal. Okay, each occurrence of variable or its complement. Okay, the variable can be, for example, if I am taking the variable a, okay, the variable a will become same as a in the Boolean expression or the complemented version a dash or a prime. Okay, each letters considered as literals. Okay, so consider this example, the Boolean function f of x, y, z. Okay, x comma y comma z. This is my example function. So this function is expressed as x and with y plus y and with x prime plus x prime and z. Okay, so here x, y, again there is a y. Okay, so this y considered as one literal, this y considered as separate literal. Okay, so here the y variable comes twice, even though the literal count will be 2. Okay, so like that you can consider this is first literal in this expression, second literal in this expression, third literal. Okay, consider this y, y. Okay, same variable but consider as separate literals. Okay, then x prime another literal, z prime another literal, x prime is also another literal z. Okay, so here the literal positions 4, 6, right? The variable z is used to represent Boolean expression but in two forms. Okay, complement form then normal form. Okay, even though both are considered as separate literals. Okay, here also x prime x, same variable, binary variable, but it available in two form in the Boolean expression, so consider as two separate literals. Okay, x is one literal, x prime is another literal. Okay, hope you all understand this concept, right? So here in this Boolean expression we have 6 literals. Then the next term is constant. Okay, constant is a value that does not change. Okay, it is a fixed value. Either it may be 0 or 1. Okay, so consider this expression y equal to a plus 1. The another expression y equal to a plus 0. Okay, in this both expression 1, 0, these two values are called as constants. Okay, here the a is variable but 1 and 0 both are a fixed value, that is constant values. Okay, this a variable may have values either 0 or 1, but this constant 1, 0 does not change, right? So logic 1 means logic 1. Okay, it does not change to logic 0 while operating the equation. Okay, any doubts? Any doubts so far?
Sir, Selva sir.
Yes, ma'am.
Sir, there was one question from Rizwan sir 10 minutes ago. Sir, what is the need for masking and unmasking?
Okay. Yes, I told no. Masking means which is used for hiding the data. Okay. If I want to send some information from sender side to a transmitter to receiver. Okay. So while sending some information from one place to another place through some channel, right? So while doing that, third party can access that particular data. Okay, through this channel, some third party may access that particular channel and reuse that data. Okay, but so to avoid that condition, okay, to improve the security on transmission, so we will follow certain procedure to hide some kind of data. Okay, so this is the purpose of masking. Okay, masking means we are hiding the certain data while sending through the channel. Okay. This one, is it okay?
Yes, sir. He replied, sir. Okay, sir.
Okay. Then the next important concept in the Boolean algebra is duality principle. Okay, so duality principle is nothing but interchanging the logical operations. That means AND operation can be interchanged to OR operation and vice versa. Okay, and all constants, zeros become ones, one become zeros. Right? Dual of the Boolean expression is obtained by interchanging all AND to ORs or ORs to AND logical operations and all constants. Okay, zeros to ones, ones to zeros. Okay, by interchanging AND operation to OR operation or OR operation to AND operation and the constant zeros to ones, ones to zeros, we will get dual of that particular logical expression or Boolean function. Okay, but the Boolean expression remains valid. Okay, for example, here a plus a prime, which is equal to 1, right? So after performing duality concept, we will get result like this. Okay, here variable a is repeated here, a prime also repeated here, but logic OR operation is interchanged with AND operation, and the constant 1 is interchanged with logic. Okay, so this is the dual of given expression. Okay, a dot a prime, which is equal to 0, which is the dual of a plus a prime, which is equal to 1. Okay, so this is the conceptual table which can be useful for performing duality principle on any given expression. Okay. So you can note this table. It may be useful for performing duality operation on Boolean expressions. Then, the most important concepts in Boolean algebra are theorems and postulates. Okay, so there are certain fixed concepts which is used in the Boolean algebra. Okay, so these theorems and postulates mostly used for minimizing the or to reducing the number of literals in Boolean expression. Okay, so theorems and postulates used to simplify the Boolean expression by reducing the number of literals and number of logical operations. Okay, so why we need to simplify the Boolean expression? Okay, with the help of these kind of theorems and postulates, right? So that will be discussed in future slides. Okay, so why we are going for simplification? Okay, so அது வந்து நம்ம next coming slides la paakalam. So before that, here we are going to see some fixed functions, okay, that are known as postulates and theorems. Okay, so these are all used for simplifying the Boolean expression. So some of the important Boolean postulates are basic assumptions or identity. So in this case, identity, x plus 0 is always is equal to x. Okay, if you are performing OR operation with logic 0, if you are performing logic OR operation with logic 0, then the result will be the given variable. Okay, the input variable will be available in the output. So x plus 0 will give x. Similarly, x and with 0 always 0. Okay, so this is identity assumption. Okay, this is first postulate or assumption. The second one is distributive law. Okay, so here x and with y plus z. Okay, so the result will be x dot y plus x dot z. Okay, so here AND operation. Okay, here the AND operation is distributed over OR operation, right? AND operation is distributed over OR operation, right? So just by multiplying each with in this expression, you will get x dot y plus x dot z, right? So x y plus x z, right? Similarly, x plus y dot z, which is equal to x plus y dot x plus z. Okay, so here the OR operation is distributed over AND operation. Okay, OR operation is distributed over AND operation. Okay, the next postulate is commutative, x dot y, which is equal to y dot z. There is no change in this expression. Similarly, x plus y, which is equal to y plus x. Okay, both results are comes under commutative law. Okay, then the complement. The next postulate is complement. X plus x prime will give logic 1. Okay, for example, if I am taking logic 0 on this binary variable x, then what is the value of x prime? This will be logic 1. If I am performing OR operation, 0 plus 1 will give logic 1. Okay, so or otherwise, if I am taking logic 1 on the x, it will give x bar as 0, then again 1 plus 0 will give same result 1. Okay, so these are all fixed assumptions. That's why it is called as postulates. X plus x bar or x prime will give logic 1 as the output. Similarly, x dot x prime will give logic 0, right? So make a note of it or take a screenshot on these postulates. It will be very helpful for minimizing the Boolean expression. Okay. So minimization of Boolean expression is most important topic in module 1. Okay, so we will give more concentration on minimization of Boolean expression. For that, we need these kind of postulates. Okay, without this postulate, we cannot perform minimization operation on the Boolean expression. So you should remember these kind of postulates while performing minimization operation. Then a Boolean theorems. Okay, so idempotency. So idempotency, the first assumption is x plus x. Okay, same variable. If you are performing OR operation on same variable, then result will be same variable. X plus x will give x. Similarly, x dot x. Okay, if you are doing AND operation on same variable, then the result will be same variable. Okay, then the next theorem, theorem 2 gives x plus 1 which is equal to 1, x dot 0 which is equal to 0. Okay, so if you are performing AND operation or OR operation with a constant, okay, so based on the logical operation, we will get different results. Okay, x plus 1 will give logic 1, x dot 0 will give logic 0. Then involution, x bar, again prime, okay, x prime on prime, right? So if you are doing complement operation twice, then you will give original variable. Okay, if I'm having variable x and we are performing complement operation twice, then you will get original variable. Okay, that means if I'm having 0, that is equal to, if I'm having the variable x, the value of this x is 0. Okay, first I am performing logical complement operation, so this 0 will become 1. Again, I am performing logical operation on this, complement operation on x prime. Okay, again what will happen? This 1 becomes 0. Okay, that will be the given data. Okay, so x prime, again prime, will give original value, right? Then associative law or associative theorem, x dot y dot z, that is equal to x dot y dot z. Okay, while performing AND operation, first you can consider these two binary variables, you can perform AND operation, then the result will be ANDed with z. Or you can consider x, y and z, perform AND operation, the result will be ANDed with x. Okay, both will be same. Okay, this is called associative theorem. Similarly, x plus y plus z, that is equal to x plus y plus z. Okay, then the fifth theorem is absorption. X plus x dot y will give x. Okay, how? Here x plus x dot y. Here you can take x as common. If I am taking x as common, then x 1 plus y. Okay, so any variable Ring with logic 1, that should be 1. Okay, then x dot 1. Okay, any variable ending with logic 1, that will give that particular variable x. Okay, so that is the theorem. So x plus x dot y, which is equal to x. Then x dot x plus y. Okay, dual of that first key, which is equal to x. So make a note of it. Then the most important theorem, De Morgan theorem. So in this theorem, we will see two concepts. One is a plus whole bar, which is equal to a bar dot b bar. Okay, a plus b whole bar, which is equal to a bar dot b bar. Okay, this is the first concept. The second concept is a dot b whole bar, which is equal to a bar plus b bar. Okay, so here you can see some example. A plus b. A plus b means we are doing OR operation on both the input data a and b, right? So a plus b. Okay, again, this is example for first case. Okay, a plus b, we are using OR gate and performing OR operation a plus b, and for bar or complement, we are including one NOT gate at the output of this OR gate. Okay, this will be equal to a bar dot b bar. Okay, so a bar dot b bar. First we are doing complement operation on each variable and we are performing AND operation. Okay, both the result will be same, right? Then again, the next one, a dot b bar. So first we are performing AND operation and NOT operation. This is equal to this one. Okay, after performing NOT operation on each variable, we can perform OR operation. Both the results are same, right? So this is the De Morgan's theorem. Okay, so these are basic rules of Boolean algebra, right? So please make a note of these basic rules. This will be very helpful while doing minimization of Boolean function. Okay, the first one is a plus 0, that is equal to a plus 1 will give logic 1, a dot 0 will give 0, a dot 1 will give the variable a plus a Okay, A or with A, ORing with same variable will give that particular variable. Then complement A plus A bar will give logic 1. Then again AND operation with the same variable will give that particular variable. Then complement of each variable A dot A bar will give logic 0. Okay, if you are performing even number of complement operation on any particular binary variable will give that particular original variable. Okay, then A plus A dot B, kind of absorption theorem. So A plus AB, which gives A, then A plus A bar B will give A plus B. Okay, then A plus B dot A plus C will give A plus BC. Right? So these are the basic rules which can be useful for minimizing the Boolean functions. Right? Then Boolean functions. Is there any doubt in the theorems and postulates? So theorems and postulates, there are some kind of assumptions. We cannot change that postulates or theorems. Okay, that are all predefined one. We have to remember all those things while doing minimization operation. Okay. Any doubt? Okay. Then Boolean functions. So Boolean function can be represented in two forms. One is using logic circuit, another one is using truth table. Okay, so logic circuit means it is a digital electronic circuit consists of basic logic gates. Okay, it may be logic OR gate, AND gate, NOT gate, XOR gate, XNOR gate, whatever it may be. Okay, with the help of logic gates, we will represent the Boolean function. Okay, the second method is truth table. Okay, so based on the function, we will define the possible combination of inputs, then corresponding outputs in a table manner. Okay, so like that you can represent Boolean function in two different forms. Okay, so consider the following Boolean function. So f of the function of a comma b comma c, which is equal to a plus b prime c. Okay, so now we are going to represent this Boolean expression using logic circuit. With the help of logic gates, we are going to represent this Boolean expression. Or you can say, for this Boolean function, we are going to draw logic circuit. Okay, so here you can note that there are two terms. Okay, so here I'm considering this is one term, this is one term. A ORing with B prime C. Okay, so first I'm taking the binary variable A, that is ORed with B prime C. Okay, so first I'm considering variable A. Okay, that going to be ORed with some second term, right? So we are using OR gate for OR operation. The plus sign represents OR operation, so we are considering OR gate here. Okay, then the second term B prime C. Okay, so in this term B is a complement of this input variable B. Okay, B prime is a complement of the input variable B. So here we are taking B and performing complement operation using NOT gate, or you can say inverter. Okay, so this will give B prime, right? Then that B prime is under with the binary variable C. Okay, so here we are using AND gate, and one of the input for this AND gate is the input C. Okay, so for this AND gate, we are providing two inputs. One is B prime, another one is C. Okay, another one is C. So this AND gate will produce B prime C. Okay, the result of this AND gate is B prime C. Okay, so this B prime dot C is the one of the input for OR gate. Okay, already this OR gate having on input A. Now we are providing second input B prime dot C. Okay, now these two inputs are together and produces the result A plus B prime C. Okay, that is the output function f. Right? So like that, you can draw the logic circuit for the given Boolean function. Okay? Hope this concept is easy to understand, right? Any difficulty in this concept? If the Boolean function is given, we need to draw logic circuit with the help of basic gates. Hope this is easy to understand. Any doubt? Then, if there is no doubt means we can move on further. Then the second representation, truth table representation. Okay, so here we are going to implement same function in terms of truth table. Okay, so we know the meaning of truth table. Okay, it consists of all the possible combination of inputs and its corresponding outputs. Okay, here we have three inputs. Okay, A, B, C. So inputs are A, B, C, and if there is a three inputs, then what are the possible combinations? 8 possible combinations. So these are the 8 possible combinations. Okay, so if you are applying these combinations on this Boolean expression, then you will get output that is equal to f. Okay, that should be either 0 or 1. Right? So that is the basic rule of Boolean function. Okay, the output should be logic 0 or 1. Right? So if you are applying first combination 0, 0, first combination 0, 0, okay, A0, B prime, okay, the value of B is 0, what about B prime? It become 1, okay, that is AND with C, the value of C is 0. So if you are considering first combination, that is 0 plus 1 dot 0. Okay, so what is the result of this combination? 1 dot 0 will give 0, that should be ORed with again 0. 0 plus 0, 0. Okay, so that is the output. So like that, you can apply these 8 combinations and obtain output function f. Okay, so this is the animation on output function f. Okay, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Like that, 8 possible combinations are applied here. Then corresponding output is obtained at the end. Hope you can understand this animation. Okay. So take this example, implementation of Boolean function using logic circuit. Okay, so here we are going to implement the given function f1 using logic circuit. Okay, f1 equal to ab plus cd plus e. Okay, so this is the given Boolean function. We need to draw logic circuit for this Boolean function. Okay, so here you can take AB as one term, CD as one term, C as another term. Okay, so if I am taking AB, this is my first term, AB. For that, I am using one AND gate. Then for second term, C AND with D. Okay, it need one more AND gate. So C AND with D needs one AND gate. Again, E. Okay, this is a single variable that is ORed with other two terms. Okay, so these two AND gate produces AB and CD term. That two terms will be ORed with E. Right? You can follow this animation, right? This AND gate produces AB, this AND gate produces CD, again ORing both the result, then we are doing again OR operation with the input variable E. Understood? Can you all follow this animation? Okay, the another example. Okay, so this is the second Boolean function. So for this second Boolean function, we need to draw logic circuit. Okay. So W prime Z plus W Z prime X plus Y prime. Okay, this is the given expression. For this Boolean expression, we need to draw logic circuit. Okay. Can you all draw this logic circuit for this Boolean function? So draw the Boolean logic circuit. Okay, so in the next session, we will discuss about the logic circuit for this second Boolean function f2. Okay, so any doubt so far? If you have any doubt, you can ask, otherwise you can leave the session.
Sir, 27 slides.
20?
Sorry, sir, 23rd, 23.
23, okay.
So I explain again, sir, Boolean theorem.
Boolean theorems, okay. So here in this slide, we have three theorems. One is idempotency, okay, then with the constant, then involution. Okay, so here idempotency, first theorem states x plus x, which is equal to x. We are performing OR operation and operation on same variable. Okay, x plus x. That means, for example, consider, sorry. Consider x equal to 0. Okay, if I am considering x equal to 0, then this x is 0, this x also 0, because same variable. We are performing OR operation on these two data, then what is the result? It will give 0. Okay, again we are getting 0, that is the value of x. Again, the another possibility, if I am considering logic 1, then 1 ORed with 1 will give logic 1. Okay, so if you are performing OR operation on both the same variable, okay, x plus x will give same variable, right? Similarly here, 0.0 will give 0. That result 0 is the value of x. Then 1.1 will give logic 1. Okay, understand this?
Yes, sir, yes, sir.
Okay, similarly here, the theorem 2. Again, if I am considering the value logic 0, okay, so if you are substituting the value for x plus 1, that will be 1. Or you can take x as 1. 1 ORed with 1, again also 1, right? So whatever may be the value of x, if that x value is ORed with logic 1, the result will be logic 1, right? Understood this concept?
Yes, sir, yes, sir.
Okay, similarly here, x dot 0. Okay, if you are doing AND operation with 0, definitely the result will be 0. If any one of the input of AND logic 0 means the output should be 0. For example, if I am substituting 0 for this x value, 0.0, result will be 0. 1.0, again the result is 0. Okay, so this is a constant theorem. Okay, it will give a constant result. There is no change.
Sir, what is the name of the second theorem, sir?
There is no name for this concept. Directly you can take this assumptions. There is no name indicated in the textbooks or reference books.
The absorption theorem, sir. Fifth theorem.
Okay, so here see here the x, if you are considering this is one term, this is another term, here you can consider as two term. In this two term the x is common. Okay, so you can take it as common term. So if you are taking x as common, then here in this position you have 1 plus x is taken out, so 1 dot y give y, so y. Okay, then again 1 plus y, if you are ORing with logic 1 with any variable, the result will be logic 1. Okay, 0 plus 1 or 1 plus 1. Okay, if you are ORing any variable with constant 1, then result will be 1. Okay, so this term will give 1, that is under with x, so x dot 1, so x dot 1 results x. Okay, so that is the result of this theorem, absorption theorem. Similarly here, so இங்க என்ன பண்ணலாம், x வந்து காமனா வெளிய எடுக்கலாம். எடுத்தா என்ன ஆகும், x 1 dot 1 plus y. Okay, so 1 plus y will give logic 1, 1 dot 1 dot 1 will give again logic 1, so x dot 1, this also equal to x. Okay, so like that we can simplify the expression, right? Understood?
Sir, this absorption where it is used, sir? Any applications for this one?
These all the postulates and theorems all are used for minimizing the expression. Okay, so here we need to directly take these theorems and postulates. Okay, we will apply these theorems and postulates in minimizing the Boolean function. Okay, which will be discussed in the next session. Right? So in the next session we will use these kind of Boolean theorems and absorptions. Okay, minimizing the Boolean.
Next slide, sir. So next slide. That basic rules. 12th on to miss sir.
Basic rules. Okay.
Yes, sir. Thank you, sir. So 1 second, sir. So thank you, sir.
Okay. Any other doubts?
No, sir. Thank you, sir.
No, sir. Thank you, sir. Bye.
Jayaprakash, Jeevan Ras, Sanjay, Manoj Kumar, Aditya, Vijay Sachin, Purushottaman,